Go.
Good afternoon, I'm Tom Immel. I'm at the AGU booth for the Naval Research Laboratory here at Fall AGU in San Francisco. I'm the principal investigator on the ICON, the NASA ICON mission. That's the Ionosphere Connection Explorer. And so my job is to make sure that that mission returns the science data that's necessary. Part of that, my job was to find the leaders in the field who could provide the science instruments, and NRL is one of those leaders. And so I'm here at the booth to see the mock-up of the MIGHTI instrument and to talk with the principal investigator, or the lead investigator of the MIGHTI instrument, Dr. Chris Englert. I shall refer to as Chris. ICON is a mission to understand the forcing, to understand the variability in the space environment near Earth, where most of our satellites fly. And it's become evident over the years that a lot of the changes in the upper atmosphere are related to forcing from the troposphere and the atmosphere below. So when we designed, we were looking for people to provide instruments. The necessary, our need was to get a good view of the boundary of space and to retrieve the winds and temperatures at the boundary of space to understand the energy that's propagating up from the lower atmosphere into the upper atmosphere, and to make those key measurements for the mission. And so MIGHTI does that, and I guess I should introduce Chris at this point to talk about the MIGHTI instrument, which we've got a mock-up here of that you printed. So Chris, I want to hand it to you.
Thank you, Tom. So as Tom pointed out, he asked us several years ago, to come up with an instrument that can measure winds and temperatures between about 90 kilometers and 300 kilometers in altitude, which is about 10 to 30 times higher than the flight altitude of normal passenger airplanes. The problem with those altitudes is you can't really have a weather balloon there, it's too high. You can't fly satellite there, it's too low. So we came up with a remote sensing instrument that looks at the naturally occurring air glow at those altitudes to measure the winds. And this is actually something that has been done before, but we have come up with a new optical technique that has some advantages. And we then came up with this instrument here called MIGHTI to measure winds and temperatures at those altitudes. So this is actually one of two optical units that we have built for the ICON satellite and delivered about a year ago for a launch in the summer of 2017. This is one out of 4 instruments that are on the ICON satellite. There's actually an image here of the satellite. You can see that here. And the way this works is that we're measuring the Doppler shift of these airglow emissions. And one of the problems with this measurement is that you have to measure a frequency change that comes from the Doppler shift that is on the order of 1 part in 10 million or so. So it's a really, really small change in frequency that we have to measure. And we do this with this instrument with an interferometric technique, with an interferometer we have a prototype of right here. And John Harlander is going to talk about that here in a minute. We also have onboard calibration lamps, and there's a little mock-up of our calibration lamp box right here. And we use that in order to calibrate on orbit regularly and make sure that our measurements are precise and deliver the right amount of information for doing the science.
The precision we asked for was, I mean, it's like if someone were running at you with a red shirt, they ran at you and you want to determine how fast they're running. His method is to determine how fast you're running by the change in the color of their shirt, which is a difficult measurement to make. A red or a green shirt. Both, we had the same requirement for both colors. So it's a remarkably sensitive instrument, and it's remarkable you can do it in this sort of small package. And the interferometer is a key part of that.
Yeah, the interferometer was designed by John, and maybe you can talk a little bit about it.
Sure. So I'm John Harlander.
I'm at St. Cloud State University and SSRC, and I've been collaborating with the Naval Research Laboratory for about 20 years on different projects. I can say this is sort of the culmination of all the projects we've done together. It's been a fantastic ride. It's been and will be going forward after we launch in June. So from an optics standpoint, which is my contribution to the project, there are 3 optical subassemblies. There's a telescope that looks out at the edge of the Earth, and that feeds light into this interferometer, which is really the heart of the instrument. And so there's an image of the edge of the Earth, what we call the limb, cast inside the interferometer. And what the interferometer does is it superimposes what we call fringes on this image of the limb. And these fringes are dark and light bands that come from the interference of the light, hence the word interferometer. The light is interfering. And it turns out that the shift of those fringes gives us a very sensitive measure, as Tom and Chris have talked about, of the speed of the atoms in the atmosphere. If they're coming towards us, there's a little tiny shift in one direction. If the atoms are going away from us, there's a little tiny shift of the fringes in the other direction. That's the fundamental measurement that we make. And then the third optical assembly, just briefly, takes the image of the limb and the superimposed fringes and casts that onto an imaging sensor, a CCD, like you might have in your phone, although it's a fancier version than you have in your phone. But then those data get sent down to the Earth, where we can do the analysis to back out the geophysical information that's used. Let me talk just a little bit about the interferometer, because that's really the technology that's most interesting part, I would say, in terms of optics. So this is, you can't see all the pieces because it's mounted in this metal housing, but there's a beam splitter in here, light comes in, and then the light splits into 2 paths. One's a little longer than the other one, and then when they recombine at the exit, that longer path, the waves of light might fall out of phase at some places, so they tend to cancel, and then in phase at other places, so they tend to add, and thereby giving us this bright and dark band pattern that we see that is very sensitive to the phase. One of the interesting aspects of this thing is that it is made with no moving parts, unlike some of the other sorts of technologies that are used for this measurement. And it can be made in a very small package and be very sensitive at the same time. Because it has no moving parts, it can be made very robust, and it's very small, and it's very sensitive, so it's a natural fit to flying in space.
So it's expensive and very detailed part, and hard to make.
Very difficult to make.
And then you get all the parts, the little pieces of glass together, you actually put them together with glue.
That's absolutely true. They're put together with adhesive, and the tolerances in terms of calibrating the optics and aligning the optics initially are roughly 1/100th the diameter of a human hair. So it's a challenging piece of optics to make, but once you make it, it's very robust.
Maybe let me say a couple of words about why this is all gold. One of the features of this is that the interferometer is very temperature sensitive. I mean, you just heard John talk about the alignment tolerances, so if it gets warm or cold, all the dimensions change, and that is something we have to account for. So we made this little enclosure that is gold coated, and the reason why we have that is that if you imagine sitting inside there and you look out at the walls and the walls change temperature, then you can see that with the radiation changing from those walls. However, if you look at a wall that's coated with gold, you really only see yourself. So you see the temperature of yourself, which then means that you're not as sensitive to the wall temperature changing. And on top of that, we're controlling the temperature of this little enclosure also with heaters and temperature sensors and a feedback loop, and that all guarantees that we don't have large temperature drifts on orbit. So
what else? Yes, and we need that because what we know now is that you're very sensitive to temperature, and that we'll expect to see some small variation in temperatures here, but
and we've
much smaller.
We've tested that in a what they call thermal vacuum chambers to make sure that we understand all the thermal properties. And I think we've seen really good results there.
Yeah.
And we're really looking forward to launching the real thing, not the printout, next summer on a Pegasus rocket into a low Earth orbit, and then get at least 2 years worth of great data from the edge of space.
What else do we need to talk about? Are we good?